In this series of videos, we are going to discuss sorting. So this continues on from the topic we discussed last week of searching and also efficiency, and we'll continue on and talk about the related topic of sorting. So sorting is the process of arranging things in a particular order, and there are lots of sorting algorithms out there. Some are very inefficient, some are much more efficient, and you can sort things in different orders. So we'll take a look at all of that. We're going to look in particular at two somewhat straightforward and easy algorithms that aren't very efficient, and we're going to look at those two algorithms in detail. And then we're going to introduce two of the more efficient algorithms, but we won't go into too much detail about those. It's more of just to give you an idea of how those sorts work. We won't actually look at the code for those more complicated sorts. Similar to search and efficiency, those of you continuing on to the next course in the Java series will delve into those details about the more complicated sorts, including the code for those sorts, but we won't deal with that in our course. So let's start out with one of the two simpler and inefficient sorts, which is selection sort. The general approach of selection sort is to find a value and put it in its final place in the list. And you do that for each value. So essentially what you do is you scan through the array or the collection, whatever you have, and you find the smallest value. Once you find the smallest value in the list, you swap it with the first position because that smallest value is going to go in the first position. Then once you're done, you have one element in its correct position. So then you start and you scan through the rest of the elements looking for the second smallest, so the next remaining smallest. Once you find it, you swap it with the second position in the list, and now you have two elements that are sorted. Then you scan through and try to find the third smallest value, and when you find it, you swap it with the third position, and now you have the first three elements are sorted. And you just keep doing that until you've gone through all the elements in your list. So again, the basic approach is to find the minimum, put it in the current spot. Find the next minimum, put it in the current spot. Find the next minimum, current, and put it in the current spot. And you just keep on doing that until you've gone through all elements in the array. Now, one important thing to note about selection sort is that when you find that, let's say that first pass through, you find the minimum and you put it in the first spot, you don't move it to the first and shift everything up. You actually just swap it with that first element. So it's not a shifting, but it's just a swap. And that's actually a common error made when tracing through selection sort. You're not shifting values, you're just taking the minimum and whatever element is in the first position and you're just swapping them. So you're just moving those two elements. You're not doing a shift of everything in between. So a note about swapping in terms of code, remember that to swap two elements in an array, for example, it requires 3 assignment statements. So you need a temporary variable to hold whatever's in your first position. Then you assign that first position to have the value of whatever's in your second position. And then you assign your second position to have the value of whatever you were storing in your temporary holder position. So you need these 3 statements in order to swap 2 values. Now, when we look at the code for sorting, we're going to be using polymorphism. So think back to when we talked about polymorphism and interfaces, and remember that we had a comparable interface that was given to us by Java. Now, when a class implements the comparable interface, that means that they implement the compare_to method. The compare_to method returns an integer, and it takes in one parameter of type object, which means you can compare the current object, or this, to any other object which is passed in as a parameter. The compare_to method returns an integer, and that integer is less than 0 if the invoking object, so this, is less than the parameter. It's 0 if they're equal, and it's greater than 0 if that invoking object is greater than the parameter. So this compare_to method allows you to order things. So it allows you to say, hey, if you give me any object, I can compare it to any other object and tell you if the current object is less than, equal to, or greater than that other object. Having that way of comparing objects allows you to sort, right? Because if we're sorting students in an array, for example, I need to know how to compare 2 students. If I'm sorting numbers, I know how to do that. But if I'm sorting students or course objects or buttons or anything else, I need to know how to compare them. What makes one student less than or greater than another? So the compare_to method is what defines that. So when you write a class, excuse me, you write the compare_to method, and that defines how 2 things are compared. So when we're writing our sorting algorithms, we're going to write them to be able to sort anything that implements comparable. So the type accepted into our sorting algorithm, our sorting method, is going to be an array or a list of comparable objects. Now, comparable is an interface, which means we can't create an object of type comparable, but we can declare an object of type comparable, and then any class that implements comparable can be sorted with that algorithm. And that'll make more sense, I think, when we look at the code. Okay? So let's take a look at selection sort. So we're going to trace through just a simple sort of some numbers, and then we're going to trace through a sort of some students. So this is the code for selection sort. So I'm going to start with my main method, just fills up an array of random numbers of 100 numbers, and then I'm going to call the selection. So I'll print it out, sort it, and then print it out again. So here's the actual code for a selection sort. So again, the sort takes in an array of comparable objects. So that means I can pass in an array of integers, an array of students, an array of any class as long as it implements comparable. Because remember, this array, this parameter rather, is compatible, will accept any compatible type. And a compatible type is any class that implements this interface. So if I say that my class implements comparable, that means that I've implemented the compare to method, and that means I can sort it with this class, this method rather. This is much better than writing a selection sort that only takes integers, and then I have to write another selection sort that takes students, and another selection sort that takes dogs, or whatever my other classes are. I don't want to have to do that. I want to write one sort, and then whatever class I want to be able to sort, I just have to make sure it implements comparable. Okay, so let's go through the actual algorithm. So there's two nested loops. The first outer loop is what goes through the array one time. So it starts at position 0, goes up to the end of the array, incrementing each time. And what we do is we say the current minimum is in that index, whatever index I'm looking at. Index 0, then it's going to be 1, then it's going to be 2, etc. I assume that the current minimum in the array is located there, in that index. And then I start at 1 past that index, and I just keep searching through the rest of the array to find the actual minimum. So for each other position in the array, I say, hey, is the element at that position in the array, is it smaller than the current minimum? And if it is, then it's the new current minimum, and this is the index of where that new current minimum is located. After I do that entire loop, I've now found the current minimum in that portion of the array that I'm looking at from index over to the end of the array. So then I swap whatever that index of the minimum is with the current index I'm looking at. And this is just a helper method of swap that allows me to swap two elements in an array. Okay, so let's trace through this. So here we've got my trace over here. This is my array. It's 10-element array, positions 0 through 9, and these are the elements that are in the array, 6, 2, 8, 1, 4, 5, 6, 7, 3, 2. So I start with my index parameter equal to 0. That's my loop, my outer loop. And I'm going to say my current min is whatever is located at that element of that index of the array. So it's 6. My current min I'm going to say is 6. And the index of min is that index. So that's here. Okay, so both index and index of min start at 0. And now I'm going to go into my inner loop or my nested loop. And I start by saying, okay, j gets the index plus 1. So j is going to be pointing to 1. Okay, and now I'm just going to go through this inner loop, and if I say if my array at position j dot compared to the current min is less than 0. This is just a way to say that array at j is smaller than the current min. So remember that if compare to returns a negative number, it means that the invoking object, array at j, is smaller than the parameter, current min. Okay, so is array at j smaller than current min? Yes, it is. So what do? I update my current min to be array at j. So current min is now going to be 2. And I update my index of min to be j. So I move this over. And then I increment my loop. So now j is incremented. And I do that same test again. Is array at j, so is 8 smaller than 2? No. So I don't go into my if statement. And then I move my inner loop forward 1. And I do the test again. Is 1 smaller than 2? Yes, it is. So now I update my current min to have the value stored in the array at j, and I update my index of min to be equal to j. And then I keep going. Is 4 smaller than So array at J is 4. Is that smaller than the current min? No. Is 5 smaller than the current min? No. Is 6? No. 7? No. 3? No. 2? No. Okay, so now I'm done with my inner loop. So now I call a swap, and I swap the values that are at position index, which is position 0, and position index of the min, which was position 3. And again, this is a swap. It's not a shift, it's a swap. So I just swap these two values. Okay? And now the first pass of my outer loop is done. So now my outer loop is going to, again, start over. Okay, so my outer loop now, my outer loop index gets incremented. Move it up. And then I get inside my outer loop and I say, okay, my current min is now 2. And my index of the min is index. Okay, now I go into my inner loop. So J gets index plus 1. And I just start going through and I do my if test. So is the array at position J 8? Is it smaller than the current min? No. So it moves up. Is 6 smaller than the current min? No. Is 4? Nope. Is 5? Nope. Is 6? Nope. 7? Nope. 3? No. And is 2 smaller than the current min? No, it's not. So my inner loop is done, and I'm going to do a swap of index and index at min. Nothing's going to actually change because those are the same. So that's my next pass through. Now I come around, I do another pass of the outer loop. So I increment index, increment the current min, increment the current index of the min, and then I get my inner loop going. So I look at, is the value at J smaller than the current min? Yes, it is. So I update the current min, update the index. And then I keep looking. Is the value at index J smaller than the current min? Yep. And update the current min, update the index. Is the value at position J smaller than the current min? No. Is this one smaller? Nope. Is this one smaller? Nope. This one smaller? Yep. So update the current min, update the index. And then is this one smaller? Yes. So update the current min, update the index. And then again, when that outer loop is done, I swap the values at index and index of the min. So I'm going to swap 2 and 8. And then my inner loop is done, so I'm ready to do another pass of my outer loop by incrementing index. So you can again see what we're doing here is now we're at the 1, 2, 3, 4th pass through. So what I'm looking for is this 4th smallest value that remains, and I'm going to swap that with my current pointer. At the next pass through, I'm going to look for the 5th smallest value that remains and swap it with my current pointer. Okay, so let's keep going. So my index is 3, the current min is 6. Index of the current min is 3. So J is 4. Is the value at J smaller than the current min? Yes. So update the current min, update the index. Is the value at J smaller than the current min? Nope. 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 Yes. So update the current min, update the index. Is this one smaller? Nope. Now I do a swap of index and index of min. And again, I'm ready for another pass of my outer loop. So I move index, update my current min, update my index of the min. J gets assigned to one position after. Is the value at J smaller than the current min? Nope. Increment it? Nope. Not smaller, not smaller, not smaller. So I'm done. I do a swap. Again, because these are the same, nothing's actually going to move. So now I'm ready for another pass of my outer loop. So I update my index to 1, update my current min to 5, index of the min to 5, and J gets the index of 6. Is the value of the array at position 6 smaller than the current min? No. Is it now? Nope. 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 I'll do a swap. Again, nothing changes. I'll increment index by 1, update the current min and the index of the min. J starts here. Is this value smaller than the current min? No. Is this value smaller than the current min? Nope. Is this value smaller than the current min? Nope. Do a swap, but nothing changes. Update the index. Update the current min. And the index of the min. is, and then j gets index plus 1. Is this value of the at j smaller than the current min? Yes, so update the current min, update the index of the min, then keep going. Is this value smaller? Nope, and I'm done. So now I again do a swap. And I'm ready for another pass of my outer loop. Index gets incremented here, current min, index of the min, start with j. Is this element smaller? Nope. So we're done. We do a swap, but nothing changes. And then I would update index to be one more. And that would be the end. And now you can see my array is in sorted order. And hopefully you get the idea of how the selection sort works. So again, the first pass through, I'm looking for the smallest element in my array. When I find it, I swap it with the 0 position. Second pass through, I'm looking for the second smallest. When I find it, I swap it with the 1 position, and so on. Okay, so that's how selection sort works. This is the code for it. You might see this code written with a little bit differences, different variable names or kind of slight differences, but this is essentially the algorithm. So when I run this, we can see I have my array of 100 random numbers. After I run selection sort, that array is sorted. Now I can also use this to sort anything else that implements comparable. So let's take a look back at, we had a student class, which is just a simple class, name, ID, and tuition, describe a student. And you can see that this class implements comparable. That means it has a compare to method, again, that takes in one object as a parameter. When you give me that object, I first of all make sure it's a student. And if it is a student, I cast it to be that. And then I'm going to start off by comparing my students based on their name. So I'm going to say, I'm just going to use the compare to method that's built into the string class to sort students based on their names. So if one name is less than the other name, then this student will be less than the other student. So my students are going to be sorted based on name. So now in my tester, what I can do is I've created 4 students, Jane Doe, Sam Smith, Al Adams, and Ray Jones, with some IDs and some tuitions. And then I just create an array of those students. And then I'm going to print out the array, sort them, and print it out again. So here we go. There's my array of students. And now they're sorted by name. So it goes Al Adams, Jane Doe, Ray Jones, and Sam Smith. It's the same selection sort method that we just used for numbers. I'm just sorting students instead of numbers. And this is the idea about polymorphism, right? Because I write one method to use this that uses this algorithm, and then I can sort any type of object that implements comparable. And it's this compare to method, the proper one will be called. So when we're sorting numbers, the way that we compare numbers will be called. When we're sorting students, the way that we compare students will be called. And if I want to change this, if I want to sort students by ID rather than by name, I could do that and rerun, and now you see these are sorted A654, K123, Q519, and Z777. So at runtime, the proper version of compare to will be called however you write it. Okay, so that is the selection sort algorithm. Now I listed a couple other video resources here. There's one, actually a good animation on Wikipedia, and there's 2 other YouTube traces. Sorting can be kind of a tricky thing to understand, so I provided you with some other materials. There are lots and lots of videos out there about sorting, but these are a couple that I think are particularly good. If you find others that you find helpful, I'm going to invite and encourage you to post them to the discussion board and share them with other students. That's in particular for the more complicated sorts, but even these, quote, simpler sorts can be a little tricky to understand. So hopefully the trace that I went through helped, but here are some additional resources if you want to watch some other people do some different kinds of traces with selection sort. For these 2 simpler sorts, selection sort and insertion sort, I do expect you to be able to trace a sort, and I do also expect you to be able to understand the code. Okay, so you should understand the coding of the sorts as well as the trace. So that's selection sort, and in the next video we will look at the other, quote, simple sort, which is insertion sort.